Hello viewers, my name is Dr. Saeed and in this video I am going to solve this fractional differential equation y double prime of x plus a times y to the power alpha of x plus b times y of x is equal to 0, where alpha is any real number lying between 1 and 2 and with these two initial conditions. So this is a fractional order differential equation because of this alpha, and this fractional differential equation has this weird looking solution, and I am going to prove it by using the Laplace transform method, which I have used many times in the previous lectures. Okay, before using that method we need to know what this y to the power alpha means. This is a fractional derivative operator. I am using this Caputo fractional derivative like I used in previous videos. So y to the power alpha is basically, this is a Caputo, put a c to remind this Caputo fractional derivative, which is 1 over gamma n minus alpha 0 integral from 0 to x minus t to the power n minus alpha minus 1 y to the power n y of nth derivative. Here n is any natural number, so this is a classical derivative of y, and then dt. Yes, here, and alpha lies between n minus 1 to n, and the Laplace transform of this Caputo fractional derivative is s to the power alpha capital Y of s, which is the Laplace transform of smaller y of x minus summation from k0 to n minus 1 s to the power alpha minus k minus 1, and kth derivative of y at the point 0. K is again an index, which is the classical derivative. So this is a concept we have used before with the same concept, but this time I've used a different notation, y to alpha order derivative. Okay, so using the Laplace transform method, we just need to apply Laplace transform on this equation and use the formula and then just proceed. Let's start. Okay, taking the Laplace transform. Okay, now applying Laplace transform on the differential equation y double prime of x. Since Laplace transform is linear operator, so we can apply it term by term. A constant, put it outside, Laplace transform y to the order of alpha of x, and then b outside, Laplace transform of y of x equal 0. Okay, the Laplace transform of this ordinary derivative is just s square. Laplace transform of smaller y of x, we can call it just capital Y of s, and then minus s times y of 0, and then minus y prime of 0. These three terms are the Laplace transform of this y double dash, and then a outside, and then using the previous formula it becomes s to the power alpha capital Y of s minus summation from k0 to n minus 1 s to the power alpha minus k minus 1 and kth derivative of y at the point 0, and then the last term b and capital Y of s is equal to 0. Okay, now using the initial conditions, which are y of 0 is c0 and y prime of 0 is c1. This becomes s square capital Y of s minus s, and y0 0 is just c0, and y prime is c1 plus a time s to the power alpha capital Y of s minus a time, and here since alpha lies between 1 and 2, which means the n, which is the next integer of alpha, here n must be 2, so n is 2, so this becomes summation k from 0 to n minus 1. Since n is 2, so it is just 1, and everything inside the infinite series will remain as it is, y with kth derivative of 0 and plus b times y of s is equal to 0. Okay, we have y of s here, y of s here, y of s here, so taking y as common, I get s square plus a times s to the power alpha, and then b, and y of s as common, and now I have c naught s and then c1 and then minus a. I need to open this series. It has only two terms, k0 and k1. When k is 0, it becomes alpha to the power alpha minus 1, s to the power alpha minus 1, and 0 derivative of y0 is just y0, whose value is c naught, so this becomes c naught. And then plus for k1, it becomes alpha s to the power alpha minus k minus 1, which is minus 2, and k1 is y prime of 0, which is c1, so this is c1 is equal to 0. Okay, now I have s square plus a s to the power alpha plus b, and outside is y of s, and I need to put everything remaining on the right hand side. Since all these terms are negative, once they are on the right hand side, all the terms become positive. So first term is c naught s and then plus c1 and then plus a time c naught s to the power alpha minus 1 and then a times c1 s to the power alpha minus 2, and from here I have capital Y of s, which is c naught s plus c1 plus a c naught s to the power alpha minus 1 and a c1 s to the power alpha minus 2, and whole over s square plus a s to the power alpha and plus b. Call it number 1. Okay, now the rest process is just to take to inverse Laplace transform on both sides and get the y back, but this is not an easy job because on the right hand side we have many terms involving s and one quadratic term which is in the denominator. Okay, so taking that out, so consider this term, so 1 over s square plus a s to the power alpha plus b, and I'm going to take common s alpha from the denominator. So s alpha is once taken out as common, the first term becomes s to the power 2 minus alpha, and from the second term only a is left, and from the last term it becomes b into s to the power minus alpha. This becomes, okay, now shifting this s alpha in the numerator, this becomes s to the power negative alpha, and from the denominator I need to again take common these two terms. So s to the power 2 minus alpha plus a, I am going to take this as common, and what is left behind in the remaining terms, it is 1 plus b s to the power minus alpha and over s to the power 2 minus alpha plus a. This is what is left behind. Okay, now the expression inside these curly brackets can be written as an infinite series. If you can really look using this series, this is 1 plus x square plus x cube plus 1. This is geometric series, infinite geometric series, whose series form is just x to the power k, sum from 0 to infinity, and this series have the sum 1 over 1 minus x, and x lies between these two numbers, -1 and -1. So this is the summation form of this series. 1 over 1 minus x can be written in this form. So using this concept, I can write this 1 over 1 plus this thing. So using that notation, I can write this thing as s to the power minus alpha, and in the denominator s 2 minus alpha plus a, and the below things becomes k from 0 to infinity. It should be 1 minus x, so my x is minus b s to the power minus alpha and whole over s to the power 2 minus alpha plus a, and this just power k. You can again take a look. 1 over 1 minus x is just x to the power k, and here my x is just negative time this thing, and again in summation form this becomes to the power k. Okay, just splitting it down, I can write it, I can shift all these terms inside infinite series because all the terms have no k, so they are independent of k. You can just put it inside the series and join the common terms. So it becomes summation k from 0 to infinity, and it becomes minus b to the power k, and then s, and s have minus alpha, and in this case it becomes minus alpha k, and one s is outside. When it comes inside, it have the same power, so joining here becomes minus alpha. Okay, in the denominator again we have the same term here and the same term here. This term has power k and this term has power 1, so combining I get s to the power 2 minus alpha plus a and whole power k plus 1. It's good now, but we need to take a little more factor common. From the denominator I'm again going to take this whole factor as common, so this becomes summation k from 0 to infinity minus b to the power k, s to power minus alpha k minus alpha, and in the denominator I will take s to power 2 minus alpha common, and since it is coming out of this whole term which have the power k plus 1, so this factor also have the power k plus 1, and what is left here, it is 1 plus a and s to the power it's in the denominator 2 minus alpha. Once it's in the numerator, it becomes alpha minus 2, and this term has power k plus 1, this thing in the denominator. Okay, now first we need to observe that this s has two powers, 2 minus alpha and k plus 1, so we will multiply these powers, and multiplying these two powers becomes 2k, and then we have 2, and then we have minus alpha k, and then we have minus alpha. Once we multiply these two factors, I will get these four terms, and then I will shift this s in the numerator where it has already one s, so we'll combine all the powers with this one, so it becomes summation k from 0 to infinity minus b to power k and s to power minus alpha k minus alpha, and these powers, once they are in the numerator, all signs will be opposite, so it becomes minus 2k and then minus 2 and then plus alpha k and then plus alpha, and in the denominator everything will be remain as it is, 1 plus a s to power alpha minus 2 to the whole power k plus 1, and now you can see that these minus alpha k cancel those minus alpha k, and minus alpha come cancel out this plus alpha, and what is left behind is just summation from k0 to infinity minus b to power k and s to power minus 2k minus 2, and in the denominator I have, or I can write just the remaining term like 1 over, need to use blue color, okay, 1 over 1 plus a s to power alpha minus 2 and this whole power k plus 1. Okay, I need to again switch this term in blue in the form of an infinite series, and what infinite series, you can again take a look. This one, we know that binomial series 1 plus x to the power n, where n is either a negative integer or fraction, it can be written as 1 plus nx plus n into n minus 1 over 2 factorial x square plus carry continuing this way n into n minus 1 and minus 2 over 3 factorial into x cube and plus so on. This process will continue so far, and if we change this x to negative z and n to negative alpha, and changing n by negative alpha and n is negative alpha and x by negative z, this takes this form, and simplifying you will get this form, and since all the negative signs cancels out, so this final expression have all the term as positive. Okay, now we'll write this in this combination and notation. So 1 is can be written as lambda plus 0 minus 1 c0. Once c is here is 0, no matter what number is here, positive number is here, this whole thing becomes 1. So this is representing just this one, and this is lambda plus 1 minus 1, it becomes lambda. Lambda c1 is just lambda, so this thing is representing by this symbol. For this we need this symbol is equivalent to this one, and for this we can do a little working here to check whether it is equal or not. So this thing is just lambda plus 2 minus 1, which is lambda plus 1, and c2, and we know that the formula of this combination symbol, it is lambda plus 1 factorial over this 2 factorial, and then lambda plus 1, difference of these two terms, lambda plus 1 minus 2 factorial. Okay, simplifying a little, in the numerator we can write lambda plus 1. Okay, opening this factorial, it becomes then lambda, and then lambda minus 1, and then stopping this factorial symbol here, and the denominator, this is 2 factorial, and this becomes lambda minus 1 factorial, and this you can see that cancels out, and what is left behind, lambda plus 1 over 2 factorial, which is same as here. It means this expression is same as this one. In the same way, we have a pattern here. You can see that if it is 0, here is 0, here is 1, here is 1, here is 2, here is 2, our two numbers remain same, and the next we have 3 and 3, and continue this process, and r term, it becomes r, and hence z to power r. So in series form, this can be written as summation from r0 to infinity lambda plus r minus 1 cr z to the power r. So this is a formula we can use to this blue term, 1 over 1 plus, but here it has minus z, so my z is negative time of this term, and my lambda is k plus 1. So using that formula, I can write summation k from 0 to infinity minus b to the power k and s to the power minus 2k minus 2, and then this thing becomes summation r from 0 to infinity, and you can see that lambda, which is the power, plus r minus 1, and here the power is k plus 1, so it is k plus 1 plus r minus 1, and here is just r, c, this symbol, and z is minus a s to the power alpha minus 2 and whole power r. Okay, now we need to simplify a little. This becomes summation k from 0 to infinity minus b to the power k and s to the power minus 2k minus 2, and then this series, this becomes summation r from 0 to infinity, this cancels out, so I'll write k plus r and then r, c minus a to power r, and then s to power alpha minus 2 into r. One more step to write, and this becomes summation k from 0 to infinity minus b to power k, and then next series summation r from 0 to infinity k plus r c r, and then minus a to the power r, and then s to the power alpha minus 2 into r, and these two powers minus 2k minus 2, and this whole thing was actually starting from s square plus a s to the power alpha plus b. So this is the final expression of this term. Okay, putting these terms back into the equation here, we started from here, so I have just found the expression for this term, and in the numerator everything will remain same. So you plugging this expression into equation 1, so from equation 1 I have y of s, capital Y of s, and then I have this series which is summation from k0 to infinity and minus b to the power k, and then I have r from 0 to infinity, k plus r, cr, and then minus a to power r, s to power alpha minus 2 into r minus 2k minus 2, and inside I have c naught s plus c1 plus a c naught s to power alpha minus 1, and then a c1 s to power alpha minus 2. Okay, now I need to put this s term inside. This is the expression. Okay, now I need to apply the inverse Laplace on both sides, and using the formula for inverse transform, and the formula, since we know that since Laplace transform of t to the power alpha is just gamma of alpha plus 1 over s to the power alpha plus 1, which means if I take the Laplace operator on here, it becomes t to the alpha is inverse Laplace transform of gamma alpha plus 1 over s to the power alpha plus 1. Since gamma alpha of alpha plus 1 is constant, we can shift it outside and we can put it in here. So this becomes Laplace inverse transform of s to the power minus alpha minus 1 is equal to t to the power alpha over gamma of alpha plus 1. I will use this formula to convert all these s into back the original function using inverse Laplace transform. Okay, applying inverse Laplace transform, I get applying L inverse on both sides, I get this one. Okay, now we get this one. Okay, now we need to separate this series, and we need also use we need to convert this c notation into factorial, and then we have to convert that factorial notation into gamma function. So multiplying this into each term, I will get 4 infinite series. Okay. Now we need to convert this notation into factorial form. This becomes k plus r factorial, and in the denominator r factorial, and then k plus r minus r, which is just k factorial. So we can put the k factorial, we can attach this k factorial with this k series, and r will remain in this r series. Okay, now look, I just arrange the series. This thing remain as it is. C naught is outside, summation here, minus p power k as it is, and now I put this x to power 2k and I join this with k series, and I put k factorial here. And for the next series are from 0 to infinity, and instead of writing k plus 1 factorial, I just put k plus r plus 1, gamma k plus r plus 1, and then r factorial in the denominator, and then I had this minus a to the power r and x to power 2 minus r, 2 minus alpha into r. So I joined them, minus alpha into x to power 2 minus alpha and whole power r, and then this denominator is just as it is. Then I put all the series in the same format, and you can see that I just joined the series with respect to their k terms and r terms. I put all the k terms with the k series and r terms with the r series, and here this is the solution which I need to prove. Hope that helps. Thank you for watching.